Hi guys, so today I'm going to be making kind of a different type of video than I normally do. This video is going to be going over work, which is topic in physics, but it's going to be a little different in that I'm going to do it the right way. Like in class you learn how to do it with all that formulas and stuff, but I'm going to explain a deeper meaning to it, a more of a fundamental understanding. So you learn in class that work work is equal to, what is it, force times displacement times cosine of theta, right? Well, where did this come from even? Because he just told you this equation out of nowhere. He just told it to you and you have to memorize it. No, it has to be coming from somewhere. It comes from the fact that work is going to be equal to force dot displacement. Now this dot here is called a dot product. Now what the dot product says is that every component of the force over here is going to be multiplied with every component of the position over here. But what also it means in a geometric, okay, so we have for the dot product we have a analytical interpretation and a geometrical interpretation. Okay, so here it is. Analytical interpretation is that, as I said before, we multiply all the components. And what do I mean by components? Let's say this f is a function of, okay, so f is a function and it's equal to let's say 2x in the I hat plus 3y in the, oh, I forgot to explain unit vectors. Okay, so before I do this, any of this, I have to explain to you the concept of unit vectors. After you learn all this stuff, it's going to be astounding how much easier physics is. Okay, so unit vectors. So in the xy plane, we have this x direction, and we have the y direction. It's a two-dimensional Euclidean space. And let's say we have a vector, like here, okay? Let's call this vector r. Now, as we learned in class, or I think we did, this vector has components. So we have r over here, has components to the right, which is the x component, so we could say r sub x. And it also has components in the y direction. Let's call it r sub y. Now these components give it, these components, the squares of them, rx squared plus ry squared. Take the square root of that, it's going to give you r. We all know this is just it's going to give you the magnitude of r. Magnitude is it looks like absolute value. This is how you represent a magnitude. You just put some, it's actually called the modulus, but you just put some absolute value lines. It's called the magnitude in physics. Okay, so we all know this, but what we don't know is what unit vectors are. Unit vectors are vectors such as r that have a magnitude of 1. So there are 3 of them that we are working with, but in this example we're only working with 2. And for high school physics we only work with 2 because we only work with in 2 dimensions, the x dimension and the y dimension. It's only 2 dimensions. But once you start going to college, you're gonna have this 3rd dimension that's popping out, which is the z dimension. Okay, so yeah, unit vectors. As I said, a unit vector such as I or j or k correspond to the axis that they project in. So the I usually goes with the x axis, the j goes with the y axis, and the k goes with the z axis. Okay? And because of this, many people sometimes refer to them as x hat, j hat, x hat, y hat, and z hat. because it goes with the x, the y, and the z. But then once you get into higher levels of physics, there are much more than 3 dimensions, and they get represented by x mu, where mu runs from 1 to like infinity. So you can't just do x, y, z, because eventually, let's say when you get up to the 30th dimension, you're going to run out of letters in the alphabet. Okay? So that's why it's customarily as I hat, j hat, and k hat. Okay? So we got this down. Oh, and they're all equal to 1. Their magnitudes are all equal to 1. So what this means is, now we can represent every vector in terms of its unit vectors. Because a vector, you can't express a vector without explaining its direction. Because a vector, as we all know, has a magnitude and a direction. And its direction is symbolized by these unit vectors. So when you were doing vectors in the first term of physics, you were not actually doing them right because they didn't have any direction. When you said north or south, those are just substitutes for these I hats and j hats. So let's look at this vector here, r. We can split it up into rx and ry. And this rx, as we just found out, is going to be in the x direction. So the x direction is symbolized by I hat. So we're going to write something like this. And this ry is in the y direction. So it's going to be symbolized by j hat. So what this means, this mathematical sentence, that means that ry in the j hat direction, or ry, r sub y, in the y direction. And same here, same thing here, we have rx in the x direction. This is what it means. Because if you just have rx, we don't know what direction it is. Because you can have components of x in the y direction. It's very possible. Okay? And then we say that the function r, not rx or ry, r is a superposition of the rx and ry. It's a linear combination. So it's going to be rx in the x direction plus ry in the j direction, or in the y direction. So this is the definition of a vector in terms of its components. Okay, so we got this down. And of course, if it was 3 dimensions, we would have r's equal to rx in the x direction plus ry in j hat plus rz, the zth component of the r vector in the z direction. No, you can't write that. In the k hat. If you're sticking with I, j, or k, you have to stick with it. You can't change. You can't have I hat, then y hat, then k hat. It has to be either I, j, k or x, y, z. Okay? So let me just clear some room here. Oh yeah, actually let's do this first. So analytical interpretation of the dot product. Dot product. So let's say we have a function, a force of 2x in the x direction plus 3y in the y direction. You see, you know what this means now. That means, okay, so the dot product with, and let's say that the x displacement is just going to be 3 in the x direction. So the analytical interpretation of the dot product means that we're going to combine all the components. And now we know that we combine components by using their I hats. We're combining their I hats and we're combining their j hats. That means combining their components. So over here you can see that I said that x is equal to 3 I hat, but I didn't say any j hat. So that means you have to automatically assume it's 0 in the j hat. If not specified, assume that it's always 0 in the j hat. Because 0, it just cancels out. So why bother writing it? So now the dot product, as I said countless times before, we multiply all the components. So let's do it. F dot x. So let's multiply the x components. What's the component in the x direction of the force? It's 2x. And what's the x component of this position? It's 3. So we multiply this 3 by 2x. It's going to become 6x in the I hat. So as you can see, we're multiplying the components. And this is essentially the dot product. And for the j hat, we're going to multiply 0 times 3y. So it's just 0 in the j hat. So this is just equal to 6x in the I hat. F dot x. So dot product is Fairly easy, we just multiply the components. And abstractly, we can write that the dot product between f and x is going to be f sub x sub x plus f sub y x sub y, which means that we take the x component of the force, we multiply that by the x component of the position plus the y component of the force multiplied by the y component of the position. Technically, it should all have vector signs here. So this is the analytical interpretation of the dot product, and now we have a geometrical interpretation. So the dot product geometrically is going to be f, the magnitude of f times the magnitude of x times the cosine of the angle between them, and that's how we got this formula for work that we saw in class. Work is actually, it is fx cosine theta, but it originates from the dot product, because the dot product has a rule. Let's just say we have any arbitrary function v and u. If we take the dot product, it's always going to be v times u times the cosine of the angle between them. And this parallels a thing called the cross product. Let's say we take the cross product symbolized by this x over here. The cross product between v and u is going to be v u times the sine of theta in the n direction, n hat. N hat just means perpendicular direction. So let's say you have a sphere, perpendicular would mean outward of the sphere. But this comes later. This comes when we're going to do some angular momentum. I'll teach you this. But right now let's just stick to dot product. Okay, so this is the basic fundamentals of dot product. We have an analytical interpretation where we multiply all the components to have the dot product, and a geometrical interpretation where we multiply the magnitudes and we take the cosine of the angle between them. So now let's apply this in some problems. Let's just do a basic problem here. It's an AP Physics B question. We have a pendulum has a mass. It's actually connected to something like this, and then it's going this way. So this is represented by its motion. Okay, so its acceleration is this way. So we'll call that positive. And they say that its mass is 0.5 kilograms. Its length, oh, this is L by the way, the length from the center to the bob, or whatever you call it. L is equal to 2 meters. And the tension, the starting tension, they say, no, I drew it the wrong way, sorry. Tension is going that way. Starting tension, we'll call it T0, is equal to 20 newtons. And this is point P, and this is point Q on the opposite side. Alright, so part A, they ask you to draw all the forces acting. Simple enough, we just draw this thing, blah blah blah. So we know we have mg down, and we know that we have, let me do this in a different color. Okay, 1 second. We have oops, yeah, that's good enough. We have mg down, and we also have tension coming from the string. Yeah, and that's basically all the forces acting on it. That is all the forces acting on it. Okay, so now part B. That was easy enough. Part B asked to find the initial velocity. How can we find the velocity here? Well, since we know the tension, we can easily find the initial velocity. Why do I say this? I say this because we know that the sum of all the forces is equal to ma, because of Newton's first or whatever second law. The net force is equal to m times a. But now a is going to be a little different, because now a is going to be a centripetal acceleration. Since it's going in a circle, it's going to have a centripetal acceleration. And just a little formula you have to know is that the centripetal acceleration is just equal to v squared over L. I'm going to learn this later on. There's many different ways to do this, but I find that using this formula is the easiest way. So we're going to get that F net is equal to m Now what's AC? AC is just V squared over L. So that's the net force of the system. So what's the net force? Well, let's see. Let's look at our free body diagram. We have, let me do it over here. Just drag it. Okay, so we have mg going down, negative mg, minus, let's make it positive. Mg down plus attention down is going to be equal to mv squared over L. Now, what I was telling you all this whole time, this is the wrong way to do it. Do not do it like this. And I'll tell you why. Because after we just learned all these unit vector stuff, we could do it so much easier way. Just watch. But this formula is good. Yeah, we need to know this formula. So I'll sum all the forces. We have mg down. Okay, so what direction is it? Is it in the x direction or is it in the y direction? Well, since it's in this direction, it's going to be in the y direction. Is it in the positive or negative? Of course, it's going down, so it's in the positive. It's in the negative direction. So we have negative mg, and what direction is that? It's in the y direction, so it's j hat. Now we have a tension also going down, so it's going to be minus a tension in the same direction, which is the y direction, j hat. And what is this going to be equal to? Since it's going down, the velocity is going to be negative quantity, so we're going to be making this equal to mv squared over L, but since velocity is negative, we're going to be making it equal to negative mv squared over L. Okay, now, since we have a j hat here and a j hat here, we can factor out a j hat, and we're just left with negative mg. You know what, technically I shouldn't write this. Since j hat is the direction, it always comes last. You see I'm writing mg here and then j hat after, because it's after it. So we could write like this, negative mg minus t in the j hat direction. You see I'm just combining the components, not multiplying it as with the dot product, combining it. It's just factoring out a j equals negative mv squared over L. And what does the question ask us to solve? It asks us to solve for the initial velocity. Technically we should be writing v0 here. So we can multiply both sides by L. We get negative mg L minus TL. I'm just distributing it in the j hat direction is equal to negative mv 0 squared. We do a little more algebra. We get v0 squared is equal to, I'm just going to divide by negative 1 real quick. So if I divide by negative 1, this cancels out. This becomes positive. This becomes positive. Since negative times negative is positive. So now we just get mgl plus TL over m. Since we could divide by m on both sides. And this is in the j hat direction. Last step, we take the square root. So v0 is going to be, and since v0 is going to be negative, since it's going down, it's going to be negative the square root of mgl. We could factor out an L. So it's just going to be L times mg plus t over m in the j hat direction. You see, using these unit vectors makes us more wary of which direction the velocity is. Because some people might think that the velocity is going in the x direction. It's completely false. It's going in the j hat direction, which of course is the y direction. So let's plug in our numbers real quick using our handy dandy calculator. Okay, so what do we have? L. What's L? L is 2 times, in parentheses, mg. M is 0.5 times 9.8 plus the tension they gave us is 20 equals, and we're dividing this by 1/2, which is the same thing by multiplying by 2, and we're taking the root of this, so it's going to be, wait, something is not right here. Something is not right. Let's just try that one more time. Yeah, it can't be right because the answer is supposed to be 10. Okay, let's see. L. Let's do L after. What's M? M is 0.5 times, what's G? G is 9.8 equals, plus, what's T? T is 20 newtons. Okay, times L. What is L? L is 2 meters. Divided by 1/2, 0.5 is equal to, Square root of that. Ah, there we go. I don't know what I did before. So 9.98 meters per second, which rounds to 10. You know what, let's put 9.98 for more accuracy. Not meters per second squared. So it's negative 9.8 in the j hat direction, but they just want the magnitude of it, and since we're taking the magnitude, it's just going to be equal to 9.98 meters per second. So when you take the magnitude of a vector in terms of the unit vectors, when you take the magnitude, the unit vector goes away, and if it's just a negative, it turns into a positive. So that's part B, we're finding the initial velocity. Part C. What is part C? Part C is to find the change in kinetic energy. So another formula you have to know is that the work done is equal to the change in kinetic energy. This is a fundamental formula that you should know. You know what, let me do this on a different paper. Okay. So we know that, as I did in the beginning of this lesson, that the work done is equal to force dot the displacement. I'm going to call it x. Now what happens if we integrate both sides? Just take the integral of both sides. So now we have that the integral, wait, no, that's not right. We have another formula for, okay, think about it like this. We have work equals force dot distance, displacement. But this is only for one particle, or one mass, right? It's only for one mass because it's only for one force, one displacement. If we have, let's say, 100 masses, we're going to have to do force 1 times displacement times displacement 1 plus force 2 dot displacement 2 times etc. until we compensate for all these 100 masses. But there's a much easier way to do this. Since we're summing these all up, we can technically say that this is a sum from n equals the first one to whatever, 100, let's say 100 in our case, of fn since n equals 1, and then 2 since fn dot xn. And a sum can always, and let's say, and we want to find a case when this this number over here, we call it n. In this case, it's 100, right? But what if it's going to infinity? We want to find the limit as these n's are going to infinity. And then the limit of the sum of f of n dot xn over all n from n equals 1 to infinity, this is going to be the limit of a sum is always an integral. So this is going to be an integral of the force, as we have here, dot, instead of x, we now have dx, which represents an infinitesimal little strip. Okay? So we've just derived this nice equation, and this, of course, let's go all the way back. This is going to be equal to the work. So the work is going to be equal to the integral of the force dot product with dx. And since it's an integral, we have to have some bounds. What are we integrating for? Since we have displacement over here, oh, this should be technically dx displacement, okay? So we have a displacement, so we're going to be integrating from the initial x position to the final x position. So this is a very important formula that we're going to use countless times. That work is the integral from x0, which is the initial position, to the final position of force dot with the displacement dx. So now let me make a new sheet for myself. Okay, we just derived that work is equal to integral from x0 to xf of force times dx. And then I said earlier that work was also equal to the change in kinetic energy. So what are we going to do right now? We're going to combine them. Yes, the integral from x0 to xf of force dot displacement dx is going to be equal to the change in kinetic energy. Oh, by the way, this is derived from the work, and this is called the work energy theorem. Just wanted to put it out there. So we combine these two equations, and we're going to be using this. And remember, part C was to find this delta x delta ke, the change in the kinetic energy. So to do this, we take this integral from the initial position to the final position of the force times dx. So let's redraw our pendulum real quick. It's going over here, and then it goes, that's not really good, and then it goes to a point. Remember I said Q, this is P. Okay, and this is its orbit, and this distance is L, has a mass m. So they want us to find the change in kinetic energy from when it goes from P to Q. And the acceleration is this way. Okay, so what do we need to do to find a change in kinetic energy? We have to solve this integral. we have to do this integral. So how do we do this integral? We need to find the initial x. So what's the initial x? So now let's do it. Okay, initial x. It's starting over here. This mass is starting over here. What direction is this mass in? It's only in the y direction. You see, it has no component in the x plane. If we call this x and we call this y, its direction is only in the y direction. So it's 0 in the I hat direction. And how much is it in the y direction? It's a distance L in the j hat direction. Because you see, if we draw some axes here, x and y, we see that this thing is centered at the origin and it goes up a distance L. So it has L in the j hat direction, and you could also see that it has no components in the x, since this whole thing is submersed in this y-axis. So this is its initial position. Now its final position. Its final position is going to be when it's over here. Okay? And we could still see it's still not in the x direction. Poor x direction is still 0. But now instead of being positive L in the j hat direction, it's going to be negative L in the j hat direction, because it's pointing downward. So if we copy it over here, we can see it's going to look like this. So it's going to be negative L because it's going down. This is the negative y direction. So it's going to be negative L j hat. Okay? When we have two unit vectors, two directions, when we take an integral from x0 to xf of f dot dx, okay, we see that this cancels out. It has no components in the x direction. It only has components in the y direction. So it's going to be the integral from x0. What's x0? It's right here. It's L. What's xf? xf is right here, negative L. Now, what's the force? Well, what's the only force acting here? The only force acting here is gravity. And what direction does gravity go? It goes down. So it's going to be negative mg. And in what direction does gravity go? It goes in the y direction. So it's going to be j hat. So the force is negative mg in the j hat direction dot d. And be careful, it's not dx anymore. It's going to be dy, because it's in the y direction. Okay? So now we have an integral from L to negative L. We want to switch that because we always want to have the lower sign on the bottom. Remember, L equals 2, so this would be the integral from 2 to negative 2. But we take integrals, let's say we have a function, we take integrals from left to right. And left has to be the negative value, and right has to be the positive value. And we can't have an integral from 2 to negative 2, that would be reversing the order. So we have to change this to the integral from negative L, whoops, my pen's not working, negative L to L, because now we have it from negative 2 to 2. So we're taking this integral, if we switch these order from L to negative L, and then to negative L to L, we have to put a little minus sign. This is just something you have to know. And then we still have this negative mg j hat dot dy. And instead of writing dy, I'm just going to write dy as a scalar. It has no vector, but I'm then just going to write its direction. And since it's dy, what direction is the y? It's the j hat direction, of course. Okay. So now we have a negative here. We can pull it out of the integral. A negative times a negative becomes a positive. So this is just equal to, I'm going to write it over there, the integral from negative L to L of mg j hat dot dy j hat. Okay. So now we take the dot product. And this I went over this for like a really long time in the beginning. To take the dot product, we multiply the components. So this is going to be the integral from negative L to L. Let's multiply the components. So we have mg and a dy. That's it. So now let's take this integral. To take the integral of something with respect to y, we're taking it with respect to dy, which means y. So mg is just a constant. M is 2, g is 9.8. We can pull it out. Pull it out. Everything that's a constant, you can pull it out. Like over here, we saw we have a negative sign, so we can pull it out of the integral because negative 1 is just a constant. We can pull it out. Mg is also a constant. So this just becomes mg times the integral negative L to L of dy. Okay? So mg stays, and then what's the integral of dy? Well, the integral of dy is just y, and this is going to be evaluated from negative L to L. Okay? So let me just drag down. Okay. So to evaluate the integral, we plug in the top one back, and then we plug in the lower one back. So we have our mg again. Mg always stays. Let's plug in the top one. We plug in the top into y. So instead of y, we have L, and then we're going to subtract this from the bottom one we plug in. So let's plug in the bottom one into y. So instead of y, it's going to be negative L. Negative is going to be positive, so it's just going to be mg times 2L. So it's going to be 2mgl. That's our answer. That's the integral that we just took. So let me give myself a new page. Okay. So we just said that the integral, we just found that the integral from x0 to xf of this force, let me write that a little better, of this force dot dx, actually it's dy because the force is only in the y direction, times this dy was equal to, what was it equal to again? 2mgl. Perfect. This is good. Why? Because we said in the beginning that the integral from x0 to xf, that work is this integral of f times dy, and we said that work is equal to the change in kinetic energy. So this thing, we know we just got it, we could plug it back, is 2mgl. And we know that this is going to be the change in kinetic energy. So now we plug in our values. 2 times m, which is 0.5, times g, which is 9.8, times L, which is 2. So the change in kinetic energy is 19.6 joules. See? We use the proper way to do this question instead of all that lousy stuff that you do otherwise. This is the proper way, using actual vectors. And lastly, we're going to do part D. Part D is to find, what is it to find? Oh yes, part D is to find the final velocity at point Q. At Q. So we know that the change in kinetic energy means 1/2 mv f squared minus 1/2 mv0 squared. And we know that the integral from x0 to xf of f dot dy is going to be equal to the change in kinetic energy. So this means that the integral from x0 to xf of f times dy is going to be equal to this 1/2, and I'm just going to pull out this common factor of 1/2 m. is going to be equal to 1/2 m times vf squared minus v0 squared. And we know that this integral is just, let me scroll down, this integral is just, what is it? We have it over here, right there, 2 mgl. So 2 mgl is going to be equal to 1/2 m vf squared. I'm just gonna redistribute it because we need to solve for vf, right? Minus 1/2 m v0 squared. Let's add 1/2 m v0 squared on both sides. We get 2 mgl plus 1/2 m v0 squared equals 1/2 m vf squared. Notice that all the masses cancel out as well. So we're left with 2gl is equal to 1/2 v0 squared. No, not equal to. Plus 1/2 v0 squared equals 1/2 vf squared. Drag this up here. I'm going to multiply everything by 2 to get rid of the fraction. Multiply this by 2, multiply this by 2. So 2 times 2 is 4, 4gl. This cancels out, just becomes 1 plus v0 squared equals, this cancels out 2, equals vf squared. And finally, vf is equal to the square root 4gl plus v0 squared. Now we just plug in the numbers. Okay, so 4 times what's g? 9.8. What's L? L is 2. Plus what's v0? v0, as we did in part A or something, we found it to be approximately 10 or 9.98. So we're going to square that. And then we take the square root of this. Okay. What? No, we did this wrong. Because why did it say square root? No, I messed up. Okay, so 4 times 9.8 times 2. Yep. Plus, what's v0? v0, 9.98 squared. There it is. Yeah, 178. And then we take the whole square root of that, which is equal to 13.34. So VF, the magnitude of VF, is 13.34 meters per second. But if we just want VF as a vector, it's going to be equal to 13.34. And since this integral is in the j-hat direction, it's going to be equal to 13.34 in the j-hat direction. So that was a basic problem, and now let's move on to the real stuff. Physics C. Okay. This problem is going to be a little more complicated, but I feel like we can do it. Okay. Yet again another pendulum though. But now it's starting from here. Okay? And then we have, it's a distance L. It's the pendulum right here, it's mass M. And then it goes down, acceleration is this way, to a point P. And of course its orbit looks like this. I can continue it forever, but I'm not gonna. So it goes to a point P. Let me draw this a little bit. It's P. And what does it ask you to do? What's part A? I don't even know myself in my notes. Okay, there it is. So part A, you just gotta draw a free body diagram. Part B asks for the velocity at point P. And then part C asks for the tension at P. Okay, so this is a basic. I mean, this is harder than the other one, but using our unit vectors, nothing cannot be solved. Let's do it. Part A, free body diagram. So we have this bob at point P. We know that mg is down, and we have a tension. Okay, part A, bam, done. Part B, velocity at point P equals what? Remember last problem we did that the integral from x0 to xf of force times dy is going to be equal to the work, which is equal to the change in kinetic energy, which is equal to 1/2 m vf squared minus v0 squared. So let's solve for this v at point P, which is vf. Oh, and another piece of advice, another thing that tells us is that it starts from rest. So this is equal to 0. So we have the integral of x0 to xf of f times dy is equal to 1/2 mvf squared. We can multiply by 2 and divide by m. So we get 2 over m times the integral from x0 to xf f dy is equal to, now this cancels out, so it's just vf squared. Okay, so we're going to use this as a starter. So let's calculate this integral. What's x0? So let's look at it. Let me just draw some axes real quick. Some dotted axes. So x-axis, this is the y-axis. And always we have to know that this thing always is at the center or the origin, 0, 0. So it is displaced to the left by an amount L. So this point is going to be negative L, comma 0. So that's our initial position. So negative L in the x direction. And this time I'm going to use x hat and y hat instead of I hat and j hat to change it up a little bit, you know. So negative is going to be negative L0 because it's displaced to the L. Is displaced L to the left since this is 0, 0. And where is it? Okay, and y is just 0. So 0 in the y direction because it's not has no components in the y direction, of course. So now xf. This is where we run into some trouble because xf is the position here. And how do we find the position here? It's not that simple, right? So we're gonna need another drawing here, a better one. So we have this center 0, 0, and we know that over here is going to be negative L. And then we have the bob at position P. And let's just draw something. Oh man, I forgot theta. This angle is theta right here between the position at P and the position to the horizontal. So this is theta. Okay, so now what do we got? We have point P and we have the horizontal. So let me just draw that real quick. This is the horizontal, or you can call it the x-axis. And we know that the x0 is going to be negative L, comma 0. So let's just draw an axis here and an axis here. No, not an axis, just some lines. And now look, this is a transversal. These two lines are parallel. So this is a transversal. That means the alternate interior angles are going to be equal. And since we know that this is L, we can see that over here is going to be L times the cosine of theta, and the opposite is going to be L times the sine of theta. So let me just draw that again. We have this pendulum starts over here, and then it's going to go over here to point P. But the length doesn't change. It's just swinging down. The length doesn't change, so this is both L. And then we just said that if we drop an axis here, not an axis, some lines here and some lines here, we know that this angle is theta because this is angle is theta. So now let's just extend this pendulum to all the way down. So this whole distance is L. So we have this whole distance is L, this distance is L at point P, and this distance is L. And then I just said that this distance is L cosine theta because it's adjacent, and this little distance over here is L sine theta. Okay? So now let's look at the x direction only. We know that this is L, this is going to be negative L, comma 0. And then if we look down here, right there, we see that from here to here is going to be L cosine theta. So to find the position over here, this is our ultimate goal, to find the position over there. So since this is negative L and this is L cosine theta, we want to find a position right there. It's going to be negative L, as we have from here, plus this L cosine theta. Since L represents the whole thing, and we're adding this cosine theta to it to find this position, comma 0, of course. So this is our projection on the x-axis, and now let's look at the y-axis. So the y-axis, this whole distance from here to here of the pendulum is going to be L. So this whole distance is L. And then I just said that over here, from here to here, is going to be L sine theta. And we're only interested in its components. So let's go back. Let me draw a new paper. Okay. Whoops. So we have this pendulum, starts from here, and then we're interested about this point here, its position, xf. Okay, so since this is a vector, we split it up into its components in the x direction. This is the vector, we split it into the x direction, so we say xf in the x direction and xf in the y direction. And we just found that xf in the x direction is going to be negative L, and then we had this L cosine theta term, comma 0. And now let's look at the y direction now. So we have this L, and then we just said it's going to be L sine of theta over there. So this xf is just going to be simply L sine of theta, since it's only displaced by L sine of theta. But this thing is not just displaced by L cosine theta, it's displaced by the whole thing minus L plus this L cosine theta, if that makes any sense to you. So finally, xf is going to be a superposition, a linear combination of the components. Remember we did before, xfx in the x direction plus xf, the y component in the y direction. Okay, so what is this x component? Negative L plus L cosine theta in the x direction, plus, what is this y component? Right here, L sine of theta in the y direction. Actually, technically, this is wrong. Because in the y component, it's negative, right? Because since we have the axis, it's going this way, so it's negative. So it should be minus L sine of theta in the y direction. This is going to be xf. And x0 is just over here. It's just going to be in the x direction, so it's going to be minus L in the x direction plus 0 in the y direction. Okay, so not too bad. This is the hard part. The hard part is all done already. So let's just recap to make sure we got it all right. L sine of theta in the y direction, L cosine of theta in the x direction. But it's not L cosine theta, it's the whole thing L minus this cosine theta. You may be confused by this negative L plus L cosine theta, but look, it's just going to be this whole thing L minus this little part L cosine theta. It's going to be L minus L cosine theta, but it's in the negative direction, so we have to put on a minus on all of this. So then when you distribute it, it's going to be negative L plus L cosine theta. That's how we got this far. Okay, so now we can take our integral finally. The hard part is always finding the positions, the initial position, the final position. So from x0 to xf of x times dy. But now we run into some problems again, because we have components in the x direction and components in the y direction. And how do we take the integral of two components in one integral? The key here is that we split it up into two different integrals. We split it up into x0 to xf, but this time in the x direction, and then we're going to add to it the y direction. Just like that. Okay? Because an integral, it also has components. This dy, or whatever it is, it's called dr, because r can be a function of x, y, z, etc. You could always split it up into its x components, y components. So you can split it up into many integrals. So let's do this integral. This is only the x components. So let's look at the x components right here and right here. The lower bound is going to be x0. x0 is going to be integral negative L. Bam. xf, the top bound. Negative L plus L cosine theta. Of what? What is it going to be? What's the force? The force is, remember from last time, is just negative mg in the y direction. So negative mg in the y direction times dot, should I say, with dx. But what direction is dx in? Dx is in the x direction. So this is going to cause some interesting outcomes. Okay, plus the integral. Now it's going to be y. So let's look at the y components. Bam and bam. Negative L sine of theta. Oh, that's xf. Wrong. So be careful. We're starting from x0. x0 is 0 in the y direction, and xf is negative L sine of theta. What's the force? Negative mg in the y direction dot dy in the y direction. Okay. So let me rewrite that real quick. Okay, so I've just rewritten it over here. Integral from x equals 0 to x equals f of f times d dot dr, since r is going to be a representation of the x and y. So we have this integral plus this integral, since this one is in the x and this was in the y. So let's evaluate it, and then we're done. So let's take the dot product. As I said before in the beginning of the lesson, the dot product, the analytical interpretation, we are going to multiply the components. So let's see what we get. Aha, we have a y component on the left, dot an x component. So let's just rewrite that real quick. It's from negative L plus L cosine theta. Let's rewrite all the components. So for this function, what is the x component? Since I did not write any x component, that means it has no x component. And if you remember, this is the force of gravity representation, and the force of gravity has no x component. So its x component is 0 in the x direction minus mg in the y direction dot dx in the x direction, as it's dx, so it has no y direction, so plus 0 in the y direction. And let's do the same thing for the other side. Actually, we don't need to, since everything is in the y. That means there is no x components. So we don't even have to write it, because it just becomes redundant. But for this one, I just want to make a point, you know. Okay. So, the dot product, we have to multiply the components. So 0 times dx is 0. Negative mg, okay, so I should have said that a little better. X components, x hat. We multiply all the components of x hat. 0 times dx is 0. So that means there is no components in the x direction. So now let's look at the y direction. So this x's cancel out. Let's look at the y direction now. We have this negative mg times 0, which is also 0. So this whole thing is just 0. So this whole integral cancels out, because the integral of 0 is just 0, of course. And that's pretty cool, because now it gives us, we can make another law. Y hat, and so let's say any function f of x in the y hat direction, let me write it over here. We could make another law for this. Or not a law, just like a rule. So if we have any function in the y hat direction dot with any function in the x direction, since the y hat dot, since the first one is only in the y direction and the second one is only in the x direction, when we multiply their components, it's always equal to 0. And this leads us to the conclusion that y hat dot x hat is 0. Ta-da! And that's a powerful theorem that you use later in vector calculus. Okay, but that's just a quick derivation. So now we're left with this integral over here. 0 to negative L sine of theta, negative mg y hat dot dy y hat. And since we multiply the components and they're the same, so we can multiply it. So 0 to negative L sine of theta. So let's multiply the components. Negative mg and then dy. So that's all we're left with. And once again, we have the lower bound is a higher number than the upper bound. And remember, we use this little trick where we need to switch the bounds. So it's going to be the integral from negative L sine of theta to 0. But if we switch it, we have to tack on this negative, right? Because the lower bound, the negative, always has to be on the bottom. It's going to be negative mg dy. And then, of course, as I said in the previous exercise, we can pull out these constants, negative mg, and a negative cancels out with this negative, just a positive. So it's going to be equal to mg times the integral from negative L sine of theta to 0 of dy equals mg, just the constants. The integral of dy, as shown in the previous example, is just y. And we're evaluating this from negative L sine of theta to 0. So let's plug in 0 as we plugged in the previous example. Not 0, we didn't plug in 0 in the previous example, but we're using the same tips. I mean, like the same tools. We're going to plug in 0, and then we're going to subtract that from negative L sine of theta when we plug it in. So we have this mg. So let's plug in 0 into y. So instead of y, we're going to have 0. And then we subtract this from when we plug in this into there. So instead of y, we're going to have negative L sine of theta. It's going to be mg times, this is positive positive, L sine of theta. So in conclusion, the work done is going to be, change in kinetic energy, is going to be L mg sine of theta. Okay? And then I said before, let's drag this up here, that change in kinetic energy is 1/2 m Vf squared minus 1/2 m V0 squared, but V0 is 0. So it's just going to be 1/2 m Vf squared is equal to change in kinetic energy, which is just this, L mg sine of theta. This cancels out, and this time they didn't give us any numbers, so we gotta be careful. We don't plug in anything. So Vf squared, we're gonna multiply by 2 on both sides, it's gonna be 2Lg sine of theta. So Vf is the square root 2Lg times the sine of theta. That's part B. And in physics C, they never give us numbers, so we gotta get used to it. Okay, we found the final velocity is square root of 2Lg sine theta using our amazing calculus. So let me just rewrite that real quick. Velocity final, or we could say velocity at P, is going to be square root of 2Lg sine of theta. Part C, they want us to find tension. So this is part B. Part C, tension equals what? So let's draw our diagram again at point P. This is P, so then we have mg down. And let's break it up into its components. So its components over here on the parallel side is going to be mg sine of theta. And its components on the perpendicular side is going to be mg cosine of theta, as we did with the, the inclined plane stuff. And since this is attached, blah blah blah, it's gonna have tension coming from there. Okay, so we can say that T minus mg sine of theta, since T is going up there and mg going down there, so it's opposite, T minus it is going to be ma, because we know that the sum of the forces is going to be ma, but this a is just not, it's not a normal a, it's going to be centripetal a. And remember I said previously, centripetal force, centripetal acceleration is going to be v squared over L. So T minus mg sine of theta equals ma, and we plug this back in, so it's going to be mv squared over L. But what's v? We just found it in part B. So T minus mg sine of theta is equal to m. What's v squared? we just square this thing. So if VF is equal to this, VF squared, when you square a radical, it just cancels out. So you're just left with 2LG sine theta. So we're going to have M times 2LG sine of theta over L. We see that the L's cancel out. What did I write here? Okay, so we have the L's cancel out. So tension minus mg sine of theta is equal to mg. Oh, 2. There's a 2 here. Why did I cancel out the 2? The L's cancel out, not the 2's. Oh man, it's been a long time. Okay, so yeah, the L's cancel out, not the 2's. So t minus mg sine of theta is equal to 2mg sine theta. Look, we have common terms. So t is equal to, we add on both sides, 3mg sine of theta. So I hope you understood that. I know it was a long video, but these concepts are very important. Thank you.